Okay, so let's get started. As far as the exam goes, it's only on chapter 14, just the equilibrium stuff that you've done since the last exam. Dr. Macedoni said there's 15 questions, 6 of them being math. So that means 9 are conceptual. So we're going to do a fair amount of conceptual and math in this review. It's open through Friday, and all the same, I'd say account for about the same amount of time you've been spending on the other tests. Braden and I put together some good problems, and we feel like this should be good preparation for the exam. So to start off, let's just talk about what is equilibrium, okay? So when we have a reaction that's in equilibrium, what is constant? The rate, or the blank of the forward equals the blank of the reverse. The rate, good. So it's not concentrations. So when we're in equilibrium, that means our forward reaction is going at the same rate as the reverse reaction. So if we're in equilibrium, are our concentrations of our reactants and products constant? Yes. They don't have to be equal, but they are constant, okay? So because the rates are going equally, the concentrations stay constant. So you're not going to have a big fluctuation in concentrations while you're in equilibrium. That was a question that was just on your sheet that you had in class today. So again, the concentrations aren't equal, the rates are equal, but the concentrations are constant while you're in equilibrium. Because we think of it as basically a net of zero. The forward is pushing as much as the reverse is pushing, so it's like a net zero is happening in the reaction. Okay? So when we talk about equilibrium, a lot of things that we've talked about is we have an equilibrium equation, an equilibrium reaction, and we disturb that equilibrium in some way. And we want to see how does the equilibrium respond to that disturbance in the equilibrium. Okay? So for our first example, we have this equilibrium reaction right here. 2NO2 is making N2O4. Okay? And then I've laid out a couple things that we're going to talk about to see how this equilibrium is going to shift. One thing to understand conceptually is that the equilibrium will always do the opposite of what you do to it. Okay, I'll repeat that. The equilibrium will do the opposite of what you do to it. So if something is in equilibrium, it's very happy, it's content. If we disturb that equilibrium, it doesn't like that, and it's going to want to do the opposite of what the disturbance was. Okay? So moving to our first example here. I add more N2O4. So I have this reaction going, and I add more N2O4. So I'm increasing this side. Okay, my equilibrium doesn't like that I added more product, so it wants to make more reactant instead. So it would shift to the left.
So you'd say that reactant shifted?
Yep, reactant shifted, shift to the left.
Reactant favored?
Not necessarily reactant favored, because we use different things for those terms.
Okay.
But we mostly just say it's going to shift towards the products or towards the reactants or left or right. Okay, another way you can think about this is think about like if you had a full bucket of water. I have a bucket of water entirely to the brim, okay? And we say when this is perfectly level, I'm in equilibrium. Now in this case, what I did is I added more N2O4. So you can think about, I tilted the bucket up to the right because I added more N2O4. Which way is the water going to spill? It's going to spill this way, right? So that's the way that your equilibrium is going to go. You can think about that. It's kind of a good visual way to think about it if that helps you. Okay? Any questions about this first one? Just adding more of something. Okay. So secondly, we increase the temperature. Now, whenever we're talking about temperature, we have to figure out first, is our reaction endothermic, exothermic? Is our heat a reactant or a product? Okay? So in this reaction, I told you the delta H is positive 126 kilojoules per mole. So my reaction is endothermic. Okay? So if my reaction is endothermic, is heat a reactant or a product? It's a reactant. So if you ever encounter something like this, just write this out on your scratch paper, and if we see immediately that this is an endothermic reaction, I'm just going to write heat out here as a reactant. It's much easier to visualize heat as being a reactant or a product, because then we see if we change the temperature, we can easily see how the equilibrium is going to be affected from that. Okay? So, I increase the temperature. Which way is the equilibrium going to shift? Left or right? It's going to shift to the right, right? So I increase temperature, I'm increasing the reactant. The equilibrium doesn't like that I increase the reactants, so it's going to want to make more products. Same thing with the bucket. I tilt it up on this side, the water is going to spill out to the left. So my equilibrium would be shifted to the right in this case. Now, one thing to note here as well, what is the only factor that affects K? Temperature, okay? Make sure you know that. Temperature is the only thing that will affect an equilibrium constant. Okay, now moving on. I have the volume of the reaction vessel, okay? So you can imagine this. I've got like a container here with this reaction happening. And I compress that container so it's half the volume, okay? If I have the volume, what's happening to the pressure there? I'm increasing the pressure. So volume and pressure are inversely proportional. So if I decrease the volume, I'm increasing the pressure. So if I'm increasing the pressure, my equilibrium reaction doesn't like that, and it wants to do the opposite of what I did to it. So in this case, it's going to want to shift to the side of more or less moles? Less moles. I increase the pressure, so it wants to make less gas moles. So in this case, it would shift again to the right. So what we're comparing here is the coefficient of our gas. I have 2 moles of gas here. I have 1 mole of gas here. If I decrease the volume, I'm increasing the pressure. My equilibrium doesn't like that. Therefore, it wants to decrease the pressure. So it shifts to the side of less moles of gas. Now, since there's so many conceptual problems on the exam, I think you'll see at least a couple of these types of problems. So just be able to know how pressure, concentration, temperature, and catalyst affect an equilibrium reaction. How do let's say I have this reaction going, I add non-equilibrium, and then I add a catalyst. What does it do? It doesn't do anything to the reaction. It won't shift left or right. The only thing a catalyst is going to do is help me reach equilibrium faster. Okay, any concepts on that right there? Just equilibrium shifts. And the 4 things that we'll do, yeah?
Does collision theory play any role in this, or is that something that we just don't think about?
Yeah, I don't think about it.
Okay.
Yep.
I think it would.
You don't have to worry, like, yes, but no. Okay, so moving on. This is a very similar question, okay? This is like a multiple choice type question that you might see on an exam. So, what is it?
It's like the Goonies are out there.
Are they dressed up or something? Okay. This question, sorry. What pressure and temperature conditions will produce the most SO3? Okay? So here's your reaction here. 2SO2 plus O2 makes 2SO3. Alright? So first of all, if we know we're talking about pressure, we're going to want to identify which side has more moles of gas. So on the left, I've got 3 moles of gas. On the right, I have 2 moles of gas. So we're going to want to keep that in mind. Okay? And they tell us here that the delta H for this reaction is negative 200 kilojoules per mole. So is heat a reactant or a product? It's a product. It's an exothermic reaction. So I'm just going to write heat in here right away. So, I want to shift my equilibrium to make more SO3. What conditions am I going to want to have that? Am I going to want to have low temperature, low pressure, or which one of these? So why don't we do pressure first? Okay? If I want to shift to this side, which has less moles of gas, what do I want to do to the pressure? I want to have high pressure, exactly. A high pressure will cause this equilibrium to shift to the right because the right has less moles of gas than the left. Okay? So, looking at this, I can immediately cross out this one and this one. So now, between B and C, we know pressure, so now temperature. If I want to make more SO3, what do I want to do to the temperature? I want to decrease temperature. Since heat is a product, if I decrease the products, the equilibrium will shift that way. So the answer here is B. Low temperature and high pressure. This is something that some form of this will probably be on your test. I can't say I know because we haven't seen the exams, but this is the perfect type of question that would assess your knowledge of how equilibriums would shift. Okay, any questions on this? Okay, let's move on then. Okay. This next one is lengthy, all right? And I came up with this problem, and I think I tried to make it really hard. So I think this is probably the hardest ice table that you've seen so far. It's harder than anything you've had in your.
You're so proud of that.
I'm really proud of this problem. I'm really proud of this problem. Okay, so this is a tough one. So I want to give you guys a few minutes to at least get started on it.
Solve this one.
Solve it, and then we'll go through it together, okay? Like, this is one that's so important for you to try it on your own and assess if you are a master of ice tables. If you are a master of ice tables, you'll get this. And if you're watching the video, pause it and do it on your own.
Oh, really?
Maybe just take it off. Yeah, dude. Those are equations that make sense. These three math problems because I think that's everyone is just and basically how they work is that help you navigate through those. And that is so for that second equation down, the ln is now a k, and the delta t on the end is now 0, so you can solve for like the delta t. The delta t naught is temperature, right? 25 degrees. But we're doing something at different temperatures, so that's why you have RT and that one would be 8.214. The only R and all the two that are not is what we figured out. You guys figured out at the bottom.
Okay. All right, let's do it.
Oh, it's going still.
It sounds like a lot of you have got it, so I'm really proud of you.
Really proud.
I'm really, really proud. So what I wanted to illustrate with this problem is something that you haven't seen before, okay? So if you understand ice tables inside and out, you should be able to solve for any variable in them. So in this one, I had you solve for an initial amount. Normally in your homeworks and the problems you've been seeing, we've been solving for equilibrium amounts, right? So I wanted to throw in a little curveball and have you solve for an initial. So when you're studying for the test, try and make your own ice tables. Like write a reaction out and fill in a couple points on the ice table, give yourself a K, and see if you can solve it out. So be able to do them backwards and forwards. So the first thing we need to do to solve this problem is to make our ice table. So let's do it. We're just going to fill in what we know from the question, okay? So the question tells us we have 0.12 atmospheres of H2. You guys mind just keeping the chatter down? I know you're really excited if you got it, you want to teach your neighbor, but for the sake of just like the video and everything. Okay, so we have 0.12 atmospheres of H2, and we have 0.26 atmospheres of I2. And the next piece of data they tell us is that we have 0.32 atmospheres of HI at equilibrium. So for my E down here, I have 0.32 of HI. So what we want to do now is figure out what change happened in this. Now normally when you're doing an ice table like this, you need to figure out first which way is the equilibrium going to shift. And had I given you all these initial values, you could have solved for the Q. Set it up like the equilibrium constant expression, solve for the Q, and then you could see if K is greater than Q, it would go to the right. If K is less than Q, it would go to the left. But because I didn't give you all of the initial data, I told you in the problem that when we equilibrate, the reaction shifts to the right. So if I'm shifting to the right, I'm making more products and I'm using up reactants. So I know here that these reactants have to be negative for the C change, and my products have to be positive. So looking at the coefficient of each of these are both just minus x and minus x. And since I'm making more products because I'm shifting to the right, this is going to be plus 2x. Okay? So now I can set up an expression for the equilibrium concentrations of H2 and I2. So this one's going to be 0.12 minus x, and this is going to be 0.26 minus x. Now this is what I'm solving for. So what I would recommend is just pick a different variable than x so you don't get confused. So I'm just going to call this y. So this is what I'm going for, okay? The next thing we need to do is write our equilibrium constant expression, which is products over reactants. I'm not going to sing the tune. Okay, so we have 43 is our Kp. I better leave myself some good room. So we have 43 equals our products over our reactants. So in this case, I already know my equilibrium concentration of HI. It's just 0.32. So this is going to be 0.32, and don't forget that it has to be squared because I have two of them there. Whatever the coefficient is in the reaction, when you put it in the expression, it has to be squared. And that's going to be divided by 0.12 minus x times 0.26 minus x. Okay? The next thing we want to do now is FOIL the bottom out. So after you FOIL the bottom out, you should get, I'm just going to erase this. 0.0312 minus 0.38x plus x squared. Now once we have that FOILed out on the bottom, we want to get this out, so I'm going to multiply both sides by all these. So I'm going to multiply this whole thing up by 43. So I'm distributing 43 to each one of these. Okay? After you do that, you should get, and simplifying that down, you're going to get 1.3416 minus 16.34x plus 43x squared equals 0.1024. That's just 0.32 squared. Now, to do the quadratic and to use your solvers in your calculator, we have to get it equal to 0. So I'm just going to subtract that over, and my final equation that I can use for the quadratic is going to be 43x squared minus 16.34x plus 1.2392. And all that is equal to 0. So now once you have it in this form, plug it into your solver. When you do that, you should get x equals 0.10466. So now, once we know our x, we can easily figure out what this is. So my end goal here is I want to find this y. I want to find the initial concentration of this. So if I have x, I can set up a little expression where y plus 2x equals 0.32. I plug x in here and then subtract it, and you should get y equals 0.11 ATM. So I felt like this was a good problem for you guys just to see something different. Now, if you really understand ice tables, it's not that hard. You just kind of have to work through it. So if you see something on your exam that you're like, how the heck do I do that? Just make an ice table and start working through it. Start working through the variables. Yes?
And how do we tell which of the two answers we get from the solver is the one we need to use?
Only one of them will work. So if you solve for one of them, what you want to do is look at these in these values, and one of them is going to make one of these negative. One of them will always make this value negative, so you know it's not that one. So, any questions on this right here? Okay. Yes?
Real quick, when can we cross out the x's?
Okay. So she just asked, when can you cross out the x's? This is what we call the assumption rule. So the rule is that if your initial concentrations of your reactants, so the things that are on the bottom in your equilibrium expression, are different by a factor of 1,000 or more of your Kp, then you can neglect it. So Braden's going to talk about it too, but basically what you do here is you take 43 divided by 0.12. If that is 1,000 or more, then you can neglect the x. If it's not 1,000 or more, you can't neglect the x, and you have to go through and solve with your solver in the quadratic. Bray's going to do it as well. Okay, any other questions about this? ICE. There's 6 math problems on this test, and yeah, probably at least a couple ICE problems. So make sure you know how to do these, backwards and forwards. Okay, I'll hand it over to Brayden then.
Okay, so as I was watching Corbin do this, I'm going to go over quickly the biggest mistakes. Biggest mistakes are forgetting to do the 2x here because of the coefficients. So remember, with rates, the coefficients didn't matter to us. We didn't deal with them unless it was an elementary step. Here in equilibrium, absolutely they matter. And so a big mistake in the tutorial lab and with students doing their homework is forgetting about that balanced equation. So don't do that, because I know a lot of you are getting really comfortable with ICE tables, and that's great. But if you miss it, it's probably because you did something small like that and not because you didn't really know what you were doing, right? And that's super frustrating. So don't forget this. The second piece is forgetting to square it as well, right, in the equilibrium expression. So that's really important. I would add as well, Corbin here was able to do this with the solver. How many of you, by a raise of hands, are using your solver in your calculator? Almost everybody. And I didn't see anyone, well, I couldn't really tell if people weren't raising your hand. It's totally cool if you're still doing the quadratic equation. We all respect you a lot. In fact, I do it. I don't even do the solver, so I guess that's valid, right? I don't use the solver. So I bring that up because if you're freaked out that you don't know how to do your solver, it's okay. But make sure when you're doing the quadratic equation that you don't screw up the signs of the quadratic equation. That's also where a lot of problems occur, okay? So most likely, you can tell a problem like this deals with some math, some algebra, that is more difficult than we've dealt with in the past. Unfortunately, this isn't a math class, and so if you're struggling with the math, but you understand how to set things up, we need to talk to you. You need to talk to your TA. Do not make a promise to us that you will not go in to take this exam and not understand how to do some of that math, right? Things like, take this entire section and why did we take it up through 43? It's not embarrassing if you don't remember those types of things, right? Or what things can cancel and what can't. It's just been a while. But let's make sure you got that crisp so you can get those points correct, all right? So transitioning into a couple conceptual thoughts that Corbin said, I really want to reiterate again that he talked about things that affect equilibrium, right? That is concentration, increasing the pressure, and also using that same word pressure, but it's a different thing, increasing or decreasing the volume. So sometimes in your problem it'll say you increase the partial pressure of something. That's basically the same as increasing the concentration of something else, and it's not talking about a volume shift. But it can use pressure and talk about a volume shift. So make sure you're looking for words like partial pressure or just pressure, okay? So those are really important, valid things that he brought up and how that affects equilibrium. He likes to say that equilibrium will shift to do the opposite from the disturbance. That's absolutely true. And it's also, his bucket example is really valid. Those of you have me, I do a cookie sheet with water example. Any example to show how equilibrium shifts with the disturbance, make sure you have that stuff down. So equilibrium, you guys, it arises from the fact that, like Corbin said, the rate of our forward reaction equals the rate of our reverse reaction. But that doesn't mean that all the concentrations are the same. That doesn't mean that everything in terms of concentration or equilibrium is right in the middle, meaning you can have a reaction that hits its equilibrium with mostly products or mostly reactants, right? So make sure you keep those ideas separate when he's talking about something conceptual. So you don't always say, oh yeah, at equilibrium, the concentrations of everything is the same, right? That's not true, just the rates, okay? And so one thing we talked about, or it's on the necessary skills list, we talked about at my recitation is how does the K constant of a rate, how is it influenced or how is it related to the K of equilibrium? Well, they're not really related, meaning they explain different things, but the best way to say it, and maybe I was wrong to say it the way that I did in my recitation, but there is a relationship that obviously when the rate of the forward equals the rate of the reverse, right? If I take the K constant for rate of the forward and divide it by the rate of the reverse, I can get the K for equilibrium, right? That is important, and so I probably botched that in my recitation, but I don't want you guys to forget that was in his slides. So whether or not he wants to test you on that, I don't know. But it is kind of how they relate, I guess, in a way. You can do it like that, okay? So we've also written these three equations out because we don't have problems specifically about these things. But that means they're probably on there as well. We just didn't take the time to do that in our hour-long review. But I want to make sure that you guys understand how to utilize these equations. First of all, between these top two, we're dealing with Gibbs free energy and two types of Gibbs free energy. Either Gibbs free energy not value, which has this little circle at the top, or the Gibbs free energy regular for the reaction. The difference between the two is one of them is a standard, meaning we're getting that value when we did this reaction at 25 degrees Celsius, or whatever the standard temperature we're going to use is. And the other delta G is for our new temperature, right? So ultimately, we can use these two equations to solve for any aspect that they don't give us, right, in the word problem. But one thing that helps us use these equations is understanding what is the value of delta G when we're at equilibrium. It's 0, right? So which delta G am I talking about in equation 2 here? What's the first one, not the second one? The second one is the delta G not value, the standard that we're getting out of the book, right? This is the one we're solving for our reaction at that moment. So if it's in equilibrium, this is 0. What does that mean about what this is inside this parentheses? Is it Q? It would be K in that instant, right? When Q is equal to K, we're at equilibrium. So look for that type of situation where you're given that problem, right? Liam, who's like an awesome TA, brought this to our attention with this top problem. He's been solving problems with this at night. Just every night he's solving problems with this equation. No, just when he ran in to tell us, he seemed like that's what he's been doing. So what he figured out, because he's so smart, was that in this equation, in order to make this work, this K value is Kc and not Kp, right? So if you have a Kp value, got to use a Kc. So you got to use the bottom equation just to manipulate them, right? Which brings us up to even one more potential goof. The R value, when we're dealing with delta G's, this is thermodynamic. So the R value is our 8.314, which means we're going to be spitting out delta G's in joules, right? But down here, this R value is the gas constant R value derived from PV equals nRT, right? So this R value is 0.08206 because this K is for a partial pressure K, right? We're dealing with something in pressures. So don't mix that up on the exam. Make sure you use the right R value. Thermodynamic R's, ATM R, right? What about T? Always in what unit? Kelvin. Make sure you do it in Kelvin, okay? So just write these down and look for practice problems with these three to get familiar. They're usually a plug and chug situation, but you do have to extract some information from the question set. Yeah.
Why does our smart problem Friday says that in the equation delta G not equals negative RT ln K relates to the value of Kp, not Kc?
So that's the problem I think he's talking about. He's saying, like, in order to get that, you can't use a KP. He came in and was like, I've been trying to solve this problem. He said it was on SmartWork. So that's what he said. He says he can't get the problem right if he does it with the KP. And if that's false, I'll send an email. But that's, Liam said, make sure you say that. He's very confident. So.
Are all of these equations on the equation sheet?
They all are except for this one. That one is not on the equation sheet. Now, this value, delta N, what is that? Change in moles. Now, we all know this one now. We're familiar because you were asked to use it on the last recitation quiz, right? But it wasn't put on your equation sheet. So just be familiar with that. This is change in moles. And when you say change in moles of what? Like change in moles of your products minus the reactants. Yeah. Caitlin.
So the G reaction, that's the one that has to be Kc, not Kp.
Yes. According to Liam, this one has to be that. And that's all the information that he gave me. I haven't personally gone through that. I promised him that I would say that.
you explained delta G at equilibrium with 0. Which equation were you talking about again? Okay, and it's that delta G.
Yeah, that. Okay.
So if you were talking about the reverse of an equilibrium equation, how would that affect the bottom formula?
Doesn't. It shouldn't affect it. It shouldn't affect it. Okay, we're going to move on.
It does. The change in moles.
Okay,
would be
it's
split.
reverse then.
Change in
Well,
moles.
if you're looking at reverse, then it's still products minus reactants either way, right? Just you have different products now, so it didn't really change. But it just changes in terms of how you're looking.
Doesn't it change your K to?
You have to inverse the K as well. This equation doesn't change, right? You have to look at the things from the right direction. That's up to you. The equation doesn't change. Okay, let's talk about this for a minute, okay? So an important thing is understanding values of K. So an equilibrium expression, we've done this a bunch. It says that we have the concentration of our products over reactants. Okay, awesome. So if I get a K value for an equation and it's really big, that tells me a lot about that equation. It tells me that that equation, that process runs almost to completion. It gives me a high percent yield. And a high yield basically for my product, meaning I form a lot of products. Because if the K value is really big, then this numerator must be a lot larger number than my denominator. But if my K is really small, I know that I actually don't produce that much product, right? And that is the situation where I want to talk about neglecting your X values, okay? So in a standard equation of something like this, A plus B gives me C, some equation, right? If I knew my initial amounts, and let's say there's something like 0.11 and something like 0.20. I know that I started with 0, so ultimately I'm shifting towards the right to make more products. This would be a minus X, we would get X, right, over here. And so our equilibrium expression would be X over 0.11 minus X times 0.20 minus X. Okay, is equal to our K. Now, I want somebody in here to yell out a very, very, very small K value.
1.35 times 10 to the negative 12.
That number might have significance for that person. They knew that number immediately, so I don't know what that is. All right, no, thank you. It's perfect numbers, perfect. Okay, so let's understand this K value. If it's super small, I know that ultimately the amount of reactant that is left at equilibrium is large comparative to the amount of product. So I start off with all these reactants, and if my K is small, barely any of them move to products. So I neglect an X in a situation where I say, I'm beginning and starting with a certain amount of my two reactants that is greater than by a factor of 1,000 at least from what my K value is. Because what I'm ultimately conceptually understanding is the fact that my K is so small, hardly any of those reactants actually go to products. So instead of actually doing all this math out, if I just say, you know what, maybe at equilibrium, if I actually did all the math out, I get something like this. 0.1099, whatever, right? Some number of like really, really close, like almost the same thing, right? So ultimately I'm like, well, it didn't really change. Maybe like so small, but not really, not enough to affect my math. So that's the case where I say, just to make it easier, I didn't really lose any at all, right? That's when I neglect the X, but make sure that it's at least by a factor of 1,000, right? At least. And so a K this small to the negative 12, and over here we have 1.11 times 10 to the negative 1, right? That's definitely a factor of 1,000, right? By a lot more, okay? So that's what we're talking about when we neglect the X. That's what that means. Okay, let's look at this problem. One of the things we need to try to understand is what happens when, like thermodynamics, we're given equations and each specific one has its own K value, and then we're going to combine those elementary steps to get some overall equation, okay? We've done a lot of problems just like this, but it was thermodynamics, and what name did we give it? Who remembers? Hess's law. Somebody said it. It's Hess's law. This is Hess's law, but for equilibrium, right? So it's not called Hess's law, but we're doing the same thing. The difference is, in Hess's law, if you remember, you were given equations. These were not k's out here. They were delta h's. So if you had a delta h of positive 16, if this was a delta h, and then I reversed this bottom equation, all I did was change the sign of Hess's law stuff. Just know that when we're dealing with k's, we don't do it at all like Hess's law for our manipulations of these sides. So it's completely different, and make sure that you have this down. Of whatever I do to this, let's see how do I manipulate the k, because it isn't like Hess's law, right? If I flip an equation with k's, I'm going to go 1 divided by that k now, versus just change some sign, right? Like I did in Hess's law. So if we look at this equation, here are my 3, I guess you could say, elementary steps. Here's my main equation down here. A plus w in equilibrium gives me c plus x, right? These are all just variables we're using, but it works. The first thing that I notice here is that the only a value that I get from all 3 of these comes from my top equation. And in my main equation, it's still on the left side. So am I going to flip my top equation? No, that would be mental. We're not going to do that. What we're going to do is look at it and say, this is the only place I get an a. Down here, my coefficient is 1. So what do I need to do to divide the top equation by to just get 1? 2, right? I got to divide everything by 2. But I'm going to tip you off for these. When I do these, the best way is to never divide. Always multiply by something. So dividing by 2 is the same as multiplying by a half, right? It's multiplying by 1 over 2. So instead of dividing all these by 2, I'm going to multiply each one by 1 divided by 2. So I'm going to take this and multiply it all the way through. The reason I want to just do multiplication is because how this manipulation works, whatever I multiply my equation by, I'm going to raise my k to that power. Because if I divided, I would want to take the root of that. So I would take the square root if it was 2. And if it was 3, I would take the cube root. But in your calculator, that gives you more of an opportunity to make a mistake. But if you just multiply by a fraction, you can easily raise things to the 1/2 or raise it to the 1/3. And notice students don't make as many mistakes when they do it like that. So you're going to raise this then to the 1/2. Okay? 21 raised to the 1/2. So that changes these values now to 1, 1/2, 1/2, and 1. Okay. Now, what do we need to do to this over here? We need to flip it because I notice x is on the left, but x needs to be on the right. And I still have just 1x here, and I have 1x here, so I don't want to multiply by anything? No. Leave it, but I got to flip it. So if I flip this equation, what do I do to this again? I go 1 divided by this number now. Okay, so that's how I change my k. Okay, what about this bottom one? What do I got to do? Absolutely nothing, right? There was nothing I needed to do. So let's see how this combines. Okay, my a just drops down. My 1/2 b canceled with my 1/2 b here. Okay, my 1d canceled with my 1d. 2 1/2 c's give me just 1 c, and my x comes down, and my w came down. So in order to get the k, what do I do at the end here? Do I add them? Do I subtract them? Multiply. And multiply. So absolutely different than Hess's law every time, right? So I multiply this out, and I get 48.5. Okay, for my equilibrium.
You multiply what?
You multiply, sorry, I should have been more specific. This one times this one times this one in their new manipulated form.
I think it's 45.8.
Sorry. It was just in my mind, completely backwards. Thank you. All right. Okay, here's some of the last stuff. We have 5 minutes or so to talk about some of this. All right. This is a lot like what Corbin was doing. This isn't complicated. In fact, it could have just been done in his section, but if you decrease the temperature of your reaction and you notice that the K also decreases, is the reaction endothermic or exothermic? How fast can you get it? Endothermic. You guys are fast. Yeah, it's endothermic. Okay, so why? Well, if I decrease the temperature, right, I know that I'm going to get some shift, but I don't know whether that is right or left. It depends on what side heat is on. What was funny? It sounded like I swore. That's bad. Okay. It must have been like really sounded like it because everyone was like. I wonder if at other colleges, like they do just swear in their reviews and stuff. I don't know. I feel like there'd be a lot of swearing in a chemistry department because people are. All right, so let's look at this. I know that if the temperature decreased, there was some shift, but I don't know which side he was on. But I do know that when I did shift that or pull temperature down, my shift was towards the left. Went to the left, and my reactance got bigger because my K got smaller, right? So that's how I know heat must have been on the left, because when I had that shift, it went left, okay? So here's the thing, you guys. If the tests haven't been working out for you, meaning you've been taking these exams, you've been trying really hard, and you almost feel like, okay, I do all the problems, and I listen to the review, and then I go and take the test, and like everything is way harder, right? What I want you to know is this. In our TA meetings, we talk with him, and he fully and truly believes that the problems on his exam were meant to be solvable with how much he's covered. He really, truly believes it. For him, he's not saying things like, that's going to be hard. He really is like, no, this is straightforward. And I know that it's not. I'm not saying that to be like, you don't know anything. What I'm trying to reiterate to you is that if you get to a problem on the exam, I want every one of your attitudes to be, okay, this is supposed to be solvable with how much that I'm supposed to know, having gone through everything and understanding and done the reading, right? It just might be at a different angle. And I think you guys would kick yourself in the pants to see, truly, if we could all see the multiple choice test again, you would go, I missed that? Oh, I knew that. But in a testing situation, I know that it's different. I know that stress is higher. Sometimes it's hard to have a clear thought process. I totally know that as a student. So just try to calm down in your exam. If you get to one of these equilibrium problems, like Corbin's, and you're like, oh, I haven't seen this, so I'm going to risk it. I'm going to miss it. Don't do that. Know that it's solvable to the level of understanding that you're supposed to have. Okay? You guys are awesome.